Hello everyone, welcome to my presentation called New Polymer Compositions for Advanced Exterior Paints. My name is İlker Kocabıyık and I am the Technical Solution Manager of Coding Business Unit in Organic Kimya. Before I start my presentation today, I would like to give you information about my situation. Today is the 7th day of my COVID-19 infection, and I would like to say sorry in advance if I need to stop, cough, or need a water break during my presentation. It's a great pleasure for me to be with you all during this event, so I didn't want to miss this opportunity. Thanks for joining, and thanks for your understandings as well. Here is the agenda of my presentation. Today, I'm going to talk about waterborne acrylics for exterior wood protection. My presentation will summarize development of a new acrylic emulsion with improved properties. Before going into performance results, I will talk about wood coating failures and the current performance of state-of-the-art acrylics. I am going to introduce you an internal tool called HP Index and talk about HP Index relationship with polymer morphology. After sharing performance test results, our newly developed acrylic, I will conclude my presentation. The performance of waterborne acrylic technologies have made big improvements in the last 15 years in developing overall required properties for exterior wood coating applications. For those properties, waterborne acrylics are now able to offer good alternatives to solvent-borne systems. Acrylics meet modern exterior wood coating's most vital performance properties for long-term protection. Those properties are water resistance, wet adhesion over variety of wood species, cold check tolerance, UV resistance, low dirt pickup, good block resistance, and color and gloss retention. Polymer industry is making acrylics for exterior paints since 1960s. Over the years, acrylic polymers have proven to be one of the best alternatives for exterior wood paints. As I mentioned, they are best today, but in a certain moment, they will fail. When we look at the failures of exterior wood coatings, we see that several different mechanisms are involved. Modern acrylics today have good level of UV resistance, gloss retention, and excellent adhesion properties. And today, we are not going to focus failures caused by those properties. We will consider all those properties are already given by acrylic backbone. This presentation today will focus on these two aspects. For the water intrusion, we are going to focus on water permeability results according to EN 927-5. And for thermomechanical properties and elasticity, we will perform cold check cycles. During my presentation, I am going to refer two market reference binders that we know for years that they are best in the balance of elasticity, outdoor durability, water permeability, dirt pickup, and block resistance. Maybe some performance properties are slightly better in one product compared to other, but both acrylics are very good according to overall performance. And both of them have proven market acceptance by majority of customers globally. The aim of our study is to utilize smart polymer design in order to achieve a water permeability resistance and cold check performance that outperforms best-in-class polymers in today's market. Elasticity of acrylic emulsions is related to glass transition temperature (TG) values. Acrylic emulsions with straight morphology can be designed with high or low TG according to monomer selection. It is a well-known fact that low TG polymers will give flexible dry films, which is definitely good for high cold check performance, but worse for dirt pickup and block resistance due to dry film tag. Increasing TG value could be a solution to avoid surface tag and achieve enough dirt pickup resistance and block resistance. But this time, we will lose elasticity and cause failure in cold check resistance. So straight acrylic morphology doesn't seem to be the right option for an acrylic binder for exterior wood. As a second option, we can use heterogeneous morphology and choose a typical core shell design where core and the shell faces have more than 20 to 30 degrees Celsius Tg differences. We might expect excellent block resistance, good dirt pickup, enough cold check performance, maybe not, but long-term outer durability will be lower due to film tension between two phases. We have targeted to use a combined approach and used other heterogeneous morphologies that may close the gaps of straight and typical core shell emulsions. During this study, several types of acrylic emulsions with varying degrees of heterogeneity were produced. For example, gradient and raspberry-like structures were taken into account. In order to better understand the implications of variations in morphology and hydrophobic balance across particles domains, a hydrophilic index is defined for the non-water miscible monomers. The method of calculating and assigning an HB index to a monomer is based on the particular solubility of that monomer in water and the solubility of water in that monomer, and multiplying the results by a factor to expand the scale to 90 in order to enhance the different behaviors of monomers when in the presence of water. As it can be seen in this figure, where only main bulk monomers are shown, the middle of the scale is MMA, methyl methacrylate, with an HB index of approximately 40. And therefore, all other monomers fall under a category of hydrophobic if they are lower than MMA and HB below 40, or under a category of hydrophilic if they are more than MMA, which is HB above 40. Similarly, any polymer can be assigned with an HB index as compared to poly-MMA. Most acrylic copolymers used in the paints are more hydrophobic than poly-MMA, which is indicated with green bar as average acrylic. And most vinyl acetate copolymers used in paints are more hydrophilic, as indicated with orange bar, as average vinyl acrylic in the figure. Achieving both film elasticity and water resistance targets with limited monomer options forced the polymer producers to work in a very narrow field of experiments. In this example, for example, we see three different heterogeneous acrylics with the same monomer compositions with varying ratios in the core and in the shell, such as 60:40, 50:50, and 40:60. Although the calculated HB index of the polymers are almost same as 30, around 30, we are able to manipulate HB index of core and shell in a wider range, and this can affect the water resistance significantly. In order to demonstrate this phenomena, free film water absorption values of polymers with varying HB indexes were plotted in this graph. The red colored line on top represents an average straight morphology acrylic with an HB index of 30, for example, an MMA and BA composition. The second red line below represents another acrylic with heterogeneous morphology, also has same HB index, but much lower water absorption values. This is a clear example of using right polymerization technique by manipulating hydrophilic and hydrophobic domains in the core and in the shell. It is possible to achieve improved water resistance with the same monomer compositions. As another example, the remaining lighter blue and darker blue lines represents three different heterogeneous acrylics with varying HB indexes. This is another example that lower HB index doesn't mean necessarily lower water absorption, and it is possible to design polymers with higher water resistance by using more hydrophilic building blocks as well. Using the techniques mentioned here, different types of new heteropolymers have been designed and produced. Typical properties of those polymers can be seen in this table. Designed polymers have varying HB index values from 24 to 31. Polymer prototypes were formulated into a typical exterior wood coating formulation, and critical performance properties of paint formulations were tested. Blocking resistance of the paints were tested with an internal method. The paints are applied to 100 micron on black PVC panels. After drying, films are stacked with 1.25 tons per meter square at 40 degrees Celsius. Blocking resistance is assessed according to 0 to 5 scale, where 0 means completely blocked paint films and 5 means there is no blocking. Lowest hot blocking resistance was obtained with market reference polymer. Internal reference P3, P4, and P5 showed better hot blocking resistance. Wet adhesion is tested on pine wood and also on solvent-based alkyd paint surfaces. After 7 days drying at room temperature, adhesion was tested by using the crosscut adhesion tester and rated with 0 to 5 scale again. Almost all tested polymers show good wet adhesion on alkyd and pine surfaces. Both P1 and P2 showed slight deficiencies. Dirt pickup was tested in lab conditions by dipping the paint panels into an iron oxide red solution and evaluating after cleaning. Evaluation is made both by visually and by measuring color difference with spectrophotometer. Delta E values indicate color difference between original white surface and the surface that is exposed to dirt. Lower the delta E value, better is the dirt pickup resistance. Best dirt pickup resistance was obtained with prototype 4, P5, with delta E values of 0.7. QUV testing according to EN 927-6 is used as an accelerated test to predict the behavior of paints under outdoor conditions. Gloss paints are applied on pine wood and dried for at least 7 days before testing. Exposure time was 1000 hours as the guidance of European Ecolabel criteria. All tested paints were good in terms of yellowing and crack formation. 60-degree gloss values were measured during testing. As shown in the figure, all paint samples have a starting gloss value of almost 60 gloss unit initially. P4 and P5 show very similar loss in gloss as market reference polymers. Both P1 and P2 showed better gloss stability, and P3 resulted in worse performance. Cold check resistance of paints are tested with the following procedure. Birch plywood panels are coated as 2 layers by brush and dried at room temperature for 7 days. And then following steps are carried out for each cycle: 6 hours water bath, 16 hours freezer at minus 10 degrees Celsius, and followed by 50-degree oven for 24 hours. After each cycle, panels are evaluated and cracks are carefully noted. Prototype 1, which has relatively lower flexibility and higher MFFT value, failed in cold check test quickly. P3 and P4 showed highest cold check resistance and outperformed both market reference polymers. Water permeability test is carried out according to EN 927-5 norm. The paint is applied 2 layers by brush on spruce wood panels. The backside and edges are sealed with 2K epoxy, and after some preconditioning steps, panels are floated in water as painted faces down for 72 hours. After 72 hours, the water uptake in grams per meter square is calculated for each test panel. Water permeability results in this figure shows that all prototype polymers showed improved values compared to market references. There is significant improvement in water permeability value in the paint made with prototype 4. Here is our summary table for all the results. When all prototypes examined individually, P1 fails in cold check cycles very early. P2 and P3 have dirt pickup issues, and water permeability improvement is not enough. In most properties, P5 looks like good. However, it cannot achieve best water permeability as well. Among all tested polymers, heterogeneous acrylic P4, which has an HP index of 27, showed significantly improved water permeability test results, as well as much higher cold check performance and low dirt pickup property. So in conclusion, HP index is a useful tool to calculate total hydrophobicity of polymer emulsions, and in some cases can be used to predict water resistance. However, a lower HB index doesn't mean a better water resistance, especially when we are designing heterogeneous morphologies. Carefully design of heterogeneous morphology has a major impact on water resistance by manipulating hydrophobic and hydrophilic domains in the polymer chain. Our study shows that by carefully rearranging polymerization parameters, composition and morphologies, there is still a narrow area for the development of a new acrylic polymer that can reduce water intrusion better than ever before, while maintaining a balanced flexibility to withstand substrate movements under changing weather conditions. In addition, keeping a tough, moderately hydrophilic surface to ensure film endurance and aesthetic properties. This is the end of my presentation. I would like to send my special thanks to a group of colleagues that has great effort behind the development of the products and preparation of this presentation. Thanks for joining our technical session. If you have any questions, I would be happy to answer you. Thanks again.
Thank you, Mr. İlker Kocabıyık. It was really interesting work, and you also make a lot of measurements and obtain a lot of results.
Thank you.
And maybe we need to discuss your results with the attendees. If you have any question, please write down in chat box, and we try to answer it. If not, maybe we can start first with me. As you mentioned at the beginning of your speech, you use market and internal reference. If you compare all your results with this internal and market, could you please explain something about these materials, internal reference? What was the main difference between them?
Yeah, basically internal reference and market reference. So we have long years of experience on the market about exterior wood protection. So those are two products from the market that proven their performance among many different customers. So that was actually our starting point during our development. So majority of the customers are happy about many different properties, all these vital properties, but of course demands are always changing and new requirements are coming. So there was the demand of keeping all these good properties same, but meanwhile improving especially the water permeability to have better levels in that EN test norm, and also if possible also to keep the excellent cold check resistance similar. So that's why we have a detailed checklist during the development of this product, and there were two successful references that we prove that our new concept will fulfill the requirements of the customers.
You mean all of your reference acrylic based and contain
Yes.
different kind of mixture of maybe monomers?
Yes, you are right, and they are already good references. So we build the new one on top of them.
Okay, thank you.
You're welcome.
Still, we don't have any question. Okay, maybe we continue one more question with me. We know in industrial use, UV coating, it's well-known technique also for the wood surface.
Mm-hmm.
If you compare this technique with your polymer products, maybe you can explain in the market of the mechanical properties especially.
Yes, thank you. Basically, there are two different areas of application. We are not producing any UV, but we have some knowledge because of the market. UVs are mostly for industrial applications where fast curing, very fast productivity is very important. So in the big factories where they produce the components for furniture or building components that every second there is a new panel is painted. So because of the rapid cure of the UV in the UV cabins, they are mostly preferred because with the solvent-borne and waterborne, this is the gap. So they are slow in drying and they are dependent on the ambient conditions. So UVs are mostly, as far as I know, for indoor applications. They are very hard and brittle. They have excellent scratch resistance, chemical resistance, hard like stone. But in our case, our developments are acrylics for outdoor coatings, and they should be soft, not as hard as UV cross-linked system. They are heavily cross-linked. So if we have such a dense cross-linking, we might have crack issues or hard surfaces for outside, because wood is moving, shrinking and swelling with humidity and also sunlight, etc. So they are a bit different concepts.
But is it possible to use water-soluble UV coating?
Could be, but they are not also common for the application area that I explained to you. They are again mostly in the industrial side, but water-soluble UVs are also common, and because of the environmental aspect, they are more and more preferred.
Yes.
So they are good systems as well.
Okay, thank you.
You're welcome.
And maybe final question. How did you apply the paints to the surface? For example, is there, do you need any special wood or any kind of wood you can use?
Basically, we try to follow the industrial standards, universal standards, and ISO 927 is the main standard in Europe for exterior wood protection. And in that standard, actually, wood types are specified in most test results, tests. For example, for water uptake, it should be spruce. So, I mean, you don't have any other choice.
Apply it without making any base coat or any additional coat?
That's a good question. So wood coating application is actually a bit sensitive. First, surface preparation is needed. So you have to sand it because wood has fibers and it's a porous surface. The sanding is crucial. After sanding and cleaning, in most cases, we directly applied 2 coat or 1 coat of application, depend on the test.
Okay, thank you very much indeed for
You're
the
welcome.
presentation.
Thank you.